In engineering, we often define a rigid body as a solid object with a perfectly definite shape and size. However, this is an idealized model. In reality, even a steel bar will deform if the applied external force is sufficiently large. These forces are constantly acting on the objects around us. While the resulting changes in shape are often too small to see, they are present in every material under load. Most of these interactions involve tensile stress, which pulls a material apart, or compressive stress, which squeezes it together. There is a third way a solid changes its dimensions. Instead of acting perpendicular to the surface, the force can be applied across it. This is a tangential force. It acts parallel to the cross-sectional area of the body rather than pushing into it. Under this force, the internal layers of the material slide relative to one another. The object undergoes a lateral shift, tilting its original vertical posture. During this specific type of distortion, the solid's overall volume remains constant. Only the geometric shape is altered as the planes slide. This internal sliding is a distinct mechanism of structural behavior, separate from simple stretching or shrinking. We define this tangential force per unit of area as shearing stress. Once that stress is applied, the next step is determining a precise way to measure the resulting physical change. In physics, we use the term strain to describe the fractional deformation caused by an applied stress. For a sideways push, this is categorized as shearing strain. While longitudinal strain measures a change in length, shearing strain requires a different approach because the object's height remains the same while its top face moves laterally. Quantifying these two values, shearing stress and shearing strain, is the baseline for calculating how structures like buildings and bridges respond to lateral loads, such as wind or seismic activity. We start with the object's original vertical height, which we label L. As the tangential force is applied, the top face moves away from its original vertical alignment. This horizontal shift is the relative displacement, denoted as delta x. Mathematically, the shearing strain is defined as this displacement divided by the original length L. This displacement also creates a clear angular change in the object's geometry. We define theta as the angle of tilt between the original vertical posture and the new slanted edge. Because the displacement is tied to these dimensions, we can evaluate the state of a solid by measuring these internal angles. Based on the right triangle formed by the shift, the ratio of delta x to L is the trigonometric equivalent of the tangent of theta. In highly rigid solids, the actual physical displacement before the material fails is remarkably small. When this angle is very small, typically less than 10 degrees, the value of tangent theta is nearly identical to the angle theta itself, measured in radians. This value, theta, represents the angular displacement of the object. To use this in engineering, we need a way to define how much a specific material resists this angular change. That property is the shear modulus, often called the modulus of rigidity, represented by the symbol G. Conceptually, G is the ratio of shearing stress divided by the resulting shearing strain. The shear modulus provides a single constant that defines exactly how much a material will resist sliding under a lateral load. We can now assemble the formal equations used to calculate these forces in structural design. We begin with the base ratio, force over area for stress, divided by displacement over length for strain. Simplifying this fraction gives us our first tool. G equals force times length, divided by area times the horizontal displacement. By applying our geometric shortcut, we replace the displacement ratio with the angle theta. This results in equation 8.11. G equals the applied force divided by area times the angle. Rearranging this solves for stress. Shearing stress equals the shear modulus times the angle. This shows that the stress required to deform a solid is a direct product of the material's inherent rigidity and the degree of the angle you are attempting to create. These equations are not just abstract math, they are the physical laws governing how matter behaves when pushed from the side. The standard unit for the shear modulus is the Pascal, or newtons per square meter. For most common materials, the shear modulus is significantly lower than the Young's modulus, often about 1/3 of the value. This means that solids generally offer less resistance to sliding and shearing than they do to stretching or compressing. Because shearing is the path of least resistance for deformation, it is the primary focus when calculating the stability of structural foundations. To see how these equations apply to a real object, we can calculate the deformation of a heavy metal slab under an extreme lateral load. We start with a square slab of lead, firmly riveted to a reinforced floor. According to the dimensions in textbook example 8.4, the slab is 50 centimeters wide and 10 centimeters thick. A massive tangential force is applied to the narrow face, 90,000 newtons. To visualize 90,000 newtons, consider the weight of 2 fully grown elephants. That is the amount of horizontal force being exerted directly against the side of the lead block. At this scale of force, a visual failure might seem inevitable. The actual result depends on lead's internal resistance to angular shifting, defined by its shear modulus. First, we calculate the area of the face receiving the force. 50 centimeters by 10 centimeters gives us 0.05 square meters. Dividing 90,000 newtons by that area results in a shearing stress of 1.8 million newtons per square meter. Next, we use the shear modulus for lead, which is 5.6 billion pascals. We plug the stress, the height of the slab, and the shear modulus into our displacement formula. The resulting calculation reveals a displacement that is nearly impossible to see with the naked eye. Under the sideways force of 90,000 newtons, the top edge of the slab moves by only 0.16 millimeters. Even with the horizontal force of 2 elephants, the metal block shifts by less than the thickness of a few human hairs. This resistance, dictated by the shear modulus, is the physical principle that allows solid matter to maintain its integrity under extreme loads.